This is Mrs. Nearing. In this video, we're going to talk through some of these questions that are mainly related to a particle level view of what's going on in a titration, which is something that's really important to understand, like what is present in the solution at various points. And we're going to look at different types of titrations here. So this first one looks like a titration curve showing a strong acid, HCl, being titrated with a strong base. So I'm going to write out the equation here. So it is HCl and NaOH, and we make NaCl and water. That would be the molecular version of this equation. The net ionic equation looks like this. We got hydrogen and hydroxide ions combining to form water. So first we want to look at what's present in the solution at various points in this curve. So initially, right here at point A, I'm starting with pure HCl. So what's present in the solution is 0.1 molar HCl. And HCl is a strong acid, so it will have completely dissociated into hydrogen ions and chloride ions. And if we see this key right here, that's where hydrogen and chloride ions look like. So it looks like this diagram showing what's happening there. Cool. I'm going to do the equivalence point next. At the equivalence point, I'm going to have just the products of this reaction. So I'm looking for one that has sodium ions and chloride ions and water, but we're not seeing, the water is not being represented. So I'm looking for one that just has sodium and chloride in it. So that looks like this one right here. So that one is C. And then at the halfway to equivalence point, I'm still going to have some HCl floating around because not all of it will have reacted, but I also will have some sodium ions floating around as well because I've added some sodium hydroxide. So that looks like I'm looking for one that contains sodium and chlorine and hydrogen. So these three things. So that looks like it would be this one right here. So this would be B. And then over here at D, what's happening here is we've gone past the equivalence point and now we're just adding excess sodium hydroxide. So what's present at part D is I've got the products of the reaction, which is sodium chloride and water, but we're not showing the water in these diagrams. But I've also added some more sodium and hydroxide. So I should see sodium ions, chloride ions, and hydroxide ions in my solution. So that looks like that's, whoops, that looks like that's this one right here. Yeah. So the chemical formula of the salt produced in the chemical reaction, that's this right here. So this reaction produces NaCl. So salt is the ionic compound that is made in your acid-base neutralization reaction. And this salt is neutral. And remember, one of the ways that we can identify if salt's going to be acid-base or neutral is if you look at that anion, Cl minus, that is the, it is a conjugate of HCl. And if HCl is a strong acid, that means its conjugate is neutral. So there's a saying that weak pairs with weak, strong pairs with neutral. So the conjugate of something strong is going to be neutral. All right, so here's another one. We got HNO3, so it's another strong acid titration. And this is kind of a stoichiometry type question. So we're looking at quantitative things. So what volume of 0.1 molar NaOH is needed to reach equivalence? So if I'm going to look at this graph, I'm going to say it looks like about 75 mils were needed to reach the equivalence point. And so based on this data, what's the concentration? Well, I'm going to write out the reaction real quick because this is a stoich problem. So here is my reaction here. Notice that my acid and base react in a 1-to-1 ratio. So therefore, that means if I can figure out my moles of base, if I can figure out how many moles of acid I must have had there. So let's see. It takes 75 mils, which is 0.075 liters of NaOH to neutralize your sample. We know the molarity of NaOH is 0.1 molar. So that means we've got 0.0075 moles of NaOH. That's how much was needed to react all of your acid. So therefore, since it's a 1-to-1 ratio, that means I must have add 0.0075 moles of acid in my original container. Do a little stoichiometry there. And then the question is, what was the concentration? So it looks like it was in a 50 ml solution. So I'm going to convert that into liters, and my moles divided by milliliters will give me molarity. So I end up with 0.15 molar. All right, here's another particle diagram. In this case, we're starting with a strong base. So if I look at what's happening here, I'm starting with KOH. I'm adding HCl to it. The products of my reaction are going to be KCl and H2O. So initially here at port A, it's going to be pure KOH, which is an aqueous ionic compound. So really it's potassium ions and hydroxide ions. So I'm going to look for a visual that's got potassium and hydroxide in it. So that looks like this one right here. I'll do this one next. So at this point B, I still have some potassium and hydroxide floating around because I still have, excess base at this point in the reaction. But I've started adding some acid, so I'm starting to make some of this product. So I'm going to have also some chloride ions floating around in there as well. And so that's going to look like, this. I have potassium and hydroxide still, but now I'll have some chloride ions as well. So I'm looking for a visual that matches that. That looks like this one right here, this first one. And then at the equivalence point, I have pure product. So at equivalence, I'm only going to have potassium and chloride ions floating around. All of my hydrogens and hydroxides will have reacted to form water. And these diagrams are leaving the water out. So I'm looking for just KCl. So I'm looking for, that looks like this one right here is just KCl. And then over here, I have kept adding acid. So this area is where we have excess acid. So I expect to have some hydrogen ions floating around in addition to what's already there, those potassium and chloride ions. So that's going to look like this one right here, D, because here's my hydrogen ions floating around. Okay. Here is the next question is, let's say we did the exact same reaction. It's still KOH and HCl, but what if we change the molarity of the HCl? This is a good question. So notice how the reaction's still the same. It's still KOH plus HCl makes water and KCl. So let's write out the net ionic equation. So the product of this reaction is still going to be neutral. So at the equivalence point, the pH is still going to be equal to 7. The only difference will be it will take less acid in order to reach the equivalence point. So if I were to sketch this out, it might look a little bit like this. Like, I'll try and freehand this. So the equivalence point is still going to be at 7. It's going to be the same as it was there, but it will take less acid to neutralize all of your base. Why? Because the acid is more concentrated in this example. Okay, here's another one. We're looking at a weak acid. And let's figure out what's going on at a particle view. So initially, you've got pure weak acid. So I'm going to look for one that only has these particles in it. So that looks like this guy right here. Boom. And then if you look at your, I'm going to write out the generic form of a weak acid titration. Okay, sometimes I find it easiest to do the equivalence point next. So at the equivalence, you're going to have pure products of this reaction. So I'm just going to expect to see some A- ions floating around. There's also going to be some sodium ions. There's going to be some sodium ions floating around as well. They're spectators, so they don't show up in this in my net ionic equation, but you'll notice that like all these other ones all have sodium ions floating around in them because they're spectator ions. They're hanging out in all these stages. Okay, so at equivalence, I just should have my anion and then my sodium. So that looks like it would be this one right here. This looks like my equivalence point. I only have those two things. If I go back and notice my equivalence point is at 60, so that means 30 is my half equivalence point. So at my half equivalence point, I should have equal amounts of my weak acid and my conjugate base present. So I'm looking for one with equal numbers of these two particles in it. And so that looks like that would be this one right here, because notice I have 1, 2, 3 acid, and I've got 1, 2, 3 of the conjugate base. So I've got equal amounts of each. And then over here at D, notice how I'm past the halfway point. So at this point, I'm going to have a little bit more. I've used up more than half of my HA. So at point D, I should have a little bit more A minus floating around than HA. So that looks like this one. I've got 1, 2, 3, 4 particles of A minus floating around, but then only 1, 2 of the acid. So this looks like it would be part D here. Whereas on part B, that's just before you've reached the halfway point. So part B, you're going to have more acid than the conjugate base present. So that looks like that would be this one right here. And then here, over here, F, when you go beyond equivalence, at this point you have added excess NaOH. So here's where I expect to see some like hydroxide ions floating around in my solution. So that's what's going on in this visual right here. All right, looking at this next one, we've got another weak acid titration. And the question is, what is the concentration of the weak acid? Well, it looks like it took 40 mils of 0.1 molar NaOH to neutralize this weak acid. And so I'm going to convert that into, I'm going to figure out how many moles that is. So my volume times molarity is going to give me moles. So that's 0.004 moles of NaOH. And it looks like the reaction isn't written out, but let's write it out real quick. These things react in a 1-to-1 ratio. How do I know that? Well, this looks like it's monoprotic, so it just contains one hydrogen. So that means that this anion must have like a -1 charge. So anyways, it's going to end up being 1-to-1 there. So there's my moles NaOH. So that means that's how many moles of acid I had. And then let's convert that into a molarity. So I had that many moles of acid, and then my volume of acid was 50 mils. So that's 0.05 liters there. So if I take my volume divided by my molarity, sorry, my moles divided by my volume, it gives me molarity. So that ends up being 0.08 molar. The approximate Ka value. So if the equivalence is at 40, the half equivalence point occurs at 20. So I'm going to look at the pH at my half equivalence point. And at this point, the pH is equal to my pKa. So it looks like the pKa for this acid is 6. Therefore, the Ka, that's the opposite of a negative log. It's to go 10 to the negative whatever. Okay, so my Ka is 10 to the -6. And then write the net ionic equation to show why the pH is greater than 7. Okay, so here's basically write the net ionic equation for this reaction. So this looks like a weak acid, and mixing it with some hydroxide, and what we leave behind is the conjugate base and liquid water. So if this is a weak acid, if we remove a hydrogen from a weak acid, what we get is a weak base, because the conjugate of a weak acid is a weak base. So weak pairs with weak, strong pairs with neutral. So that's why this titration has a pH of around like 9.3 at the equivalence point, is because the product of this reaction is a weak base. All right, so looking at one more here, this case we're titrating a weak base. So I'm starting here. This is my weak base that we're starting with. So initially at A, you have pure weak base. So that looks like this one right here. And then let's write out the reaction that's happening. So you're combining HCl and NH3. And there's two different ways we can write it. This is the molecular version of this equation. This would be the salt that we make in this reaction. This would be the net ionic version. And notice that what's happening here is, and this is a general rule of thumb that you can just always apply for all these reaction types, is that your base is being a hydrogen taker. So your base, NH3, is taking a hydrogen from your HCl there, and it forms this thing right here, NH4+. That's the product of this reaction. And, okay, so we already figured out A. Let's figure out E. At E, we should have pure products. So at point E, at the equivalence point, we should have just NH4 and Cl- ions floating around. So that would be these two guys right there. So that looks like that would be this one over there. And at the half equivalence point, you're going to have equal amounts of your weak acid and your conjugate base. So in this example, you should have equal amounts of NH4 and NH3. So that looks like, oh gosh, this one's harder to count here, right? Because they look very similar. I think that looks like one, I think that's this one. I got 1, 2, 3 of the acids, and then this one is one, I got 3 of the bases. Okay, so this is your half equivalence point right there. And this is on the AP test, if they give you particle diagrams like that, you do actually want to count them. And like that is part of what you're being asked, is like, which is an accurate representation in terms of like the relative portions of particles. So this is really good practice for that. I'm going to go through and I'm going to circle the, if I look at this graph right here, it looks like this one has more of the base than the acid. So that would fit with B over here. I haven't quite used up half of my base. I still have some extra base floating around. And then what else do I have going on? This one over here, I'm going to notice that it's got some hydrogen ions floating around in it. So the only time I get hydrogen ions floating around is if I'm beyond the equivalence point and I kept adding extra HCl. So this must correspond to, whoops, to F. And therefore this last one I can figure out is D. And we can see that that makes sense because in this one I've got 1, 2, 3, I've got 4 of these products and only 2 of the reactants left. So I've used up more than half of my original reactant. So that's why it fits with this part right here. I'm beyond the halfway point. Okay. I think this is our last one. Cool. So here's another one where we're looking at a weak base that's being titrated. So what's the concentration of the weak base here? So this is pure base. Let's see, it looks like it takes 60 mils of 0.1 molar acid to react all of our base here. So this is very similar to, was it this problem we did right here, right? It was like a little stoichiometry problem. Okay, cool. So it took 60 mils of acid. So molarity, that's 0.06 liters times 0.1 molar. So that's 0.006 moles of HCl. And they react in a 1-to-1 ratio. Here's the net ionic equation of what's happening when a weak base combines with a strong acid. Your base is going to take the hydrogen from the strong acid. So it's a 1-to-1 ratio there that they react in. And so that means I must also have had 0.006 molar of my base. And I'm going to divide that by my volume, which is 0.05 liters. And that's going to give me my molarity, which when you do that ends up being, 0.12 molar. the KB value, okay, well this is, we haven't talked about KB value yet, but we have talked about Ka. So we know at the half equivalence point, the pH equals the pKa. And that's true whether you start with the acid or the base. So what we know here is that the pKa of the conjugate acid is 10. So that's the pKa of this thing, BH+. That's the conjugate acid of that base we started with. And since there's that relationship, remember, between Ka and Kb, we say that as long as when the temperature is 25 degrees, that Ka times Kb equals Kw, which is 10 to the negative 14. So another way to think of that is pKa plus pKb equals 14. That looks an awful lot like this equation, pH plus pOH equals 14. It's a very similar relationship happening there. So if the pKa of the acid is 10, that means the pKb of the base must be 4. So the Kb value is 10 to the negative 4. So there's kind of an extra step here when you're trying to figure out the Kb. All right. And here, the pH at equivalence is 5.6. Explain why. Well, this right here, the product of this reaction is the conjugate acid of a weak base. So if B is a weak base, this right here, the conjugate of a weak base is a weak acid. And that's why it has a pH of 5.6. That's why the pH is below 7. All right. Thanks for watching. Hope that helped.